In the physical world, data does not exist in isolation. Entities naturally relate to countless other entities, forming a dense, intersecting web of constant connections. When database architects attempt to map this reality into Salesforce, they hit a strict limitation. The system natively prohibits direct many-to-many relationships at the object level. This restriction exists to ensure database integrity. Allowing unmediated dual-directional links creates a severe risk of generating orphan data and triggering infinite computational loops when records are updated or deleted. To safely map a many-to-many relationship without breaking the system, developers cannot simply draw a straight line. They must engineer a distinct structural bridge. Within the Salesforce ecosystem, this required architectural layer is formally known as a junction object. The junction object acts as a mandatory enforcement mechanism, necessary to maintain long-term relational stability within the database. Let's test this architectural constraint at the fundamental level using a schematic view. Consider two generic, independent entities that require a mutual connection. We will designate them as Object A and Object B. This diagram shows the logical attempt to link them. We try to draw a direct, dual-directional relationship, but the architecture rejects it entirely. The platform prohibits compiling a direct many-to-many schema. When the connection fails, an architectural void remains. Both objects stay completely isolated. To resolve this, we pivot the architecture, translating a single many-to-many connection into two distinct one-to-many relationships. By deconstructing the relationship into these standard components, the schema aligns with the database's core operational rules. We can ground this abstract theory by mapping it to a recognizable business use case. We will define our first primary entity, students. This ERD outlines our primary nodes. On one end, we place students, and on the opposite end, courses. The real-world business logic flowing from left to right dictates that a single student requires the ability to enroll in multiple different courses. The inverse logic flowing right to left dictates that a single course must have the capacity to host multiple different students. Because the system refuses a direct connection between these endpoints, we must deploy a central anchor to manage the data traffic. When business rules directly contradict database constraints, expanding the schema is the only viable path forward. We deploy a third custom object directly into the center of the schema. We label this structural bridge enrollment. First, we construct a formal one-to-many line originating from the students object and terminating at enrollment. We explicitly label this first connection as a master-detail relationship. The student is the master, and the enrollment acts as the detail. Next, we mirror that action to create the symmetrical second connection. We draw a one-to-many line originating from courses and terminating at enrollment. This second connection is also a master-detail relationship, defining the course as the master and enrollment as the detail. This is the ironclad rule of junction objects. They operate exclusively by anchoring these two independent master-detail relationships simultaneously. The junction object possesses zero independence. Its entire existence and behavior are entirely dictated by its two parent masters. To understand the mechanics of this bridge, we observe the granular reality of a single row of data. This diagram isolates an individual record residing within the enrollment object. Notice the two distinct empty slots labeled foreign key. The first foreign key slot functions strictly to point towards one specific student record. The second foreign key slot functions identically on the other side, pointing strictly to one specific course record. The logic is absolute. This enrollment record exists for no other reason than to lock this precise student to this precise course. The master detail setup guarantees cascading consequences. If a user deletes either the student or course master record, this enrollment record is automatically destroyed. At the granular level, the system maintains the illusion of a many-to-many connection through thousands of these simple, targeted dual pointers acting in concert. While this structural bridge ensures database stability, this specific arrangement enables advanced reporting capabilities. Looking back at our completed three-node diagram, empty numerical counters now appear on both parent objects. Salesforce provides a powerful calculation tool called Roll-Up Summary Fields. This native tool functions only because we utilized strict master detail relationships to build our bridge. Data flows upwards. The individual enrollment records automatically calculate and update the total enrolled courses counter directly on the parent student node. Simultaneously, data flows upwards in the opposite direction, updating the total registered students counter on the parent course node. The rigid architectural constraints of the Junction object provide the specific data lineage required for the system's most capable native aggregation tool. Database architects define this achieved state as bidirectional aggregation. Administrators rely heavily on this operational capability. They can query aggregated metrics on both parent objects in real time without writing any custom code. If a developer attempts to build this bridge using standard lookup relationships instead of master detail lines, standard lookups fail to achieve this dual rollup capability. The calculation logic fails. Therefore, the Junction object operates as a mandatory foundational tool for complex enterprise reporting. Strict database rules enforce elegant structural engineering. By forcing developers to intentionally construct a Junction object, Salesforce translates the chaos of many-to-many realities into a stable, highly measurable, and logically sound architecture.